Hi fellow enthusiasts, welcome back again to my channel. Let's go into today's video and we're going to come back at the end to wrap it up. So we just finished one of our extended tutorials where we demonstrated or we showed you how the amplitude shift key is applied to the R433 transceiver circuit or the transmitter circuit. Now we're going to concentrate on the receiver circuit. So the entire video is on the transceiver circuit. So the transmitter and the receiver combination, and you can use this to build a walkie-talkie. And we're trying to show you how you can do that. Now we finished the transmitter circuit and showing you how to convert the ASK into a regular transmitter by modulating it with an audio signal. And then we also went in depth to show you that you can use a PNP transistor in place for converting the R433 transmitter into a circuit that can be controlled by a negative going signal. In this circuit, we're going to be showing you, in this episode, we're going to be showing you how to modify the receiver. The current receiver as it is designed is not optimized for audio signal. It is designed for remote or control devices. As we showed you in the transmitter, there's no audio signal connected in any way. So you just send a burst of RF signals, which is interpreted as a 1 at the receiver. How is this achieved? We're going to show you how this is achieved. We're going to define the theory of the Schmitt trigger, which is what is basically used to convert this burst of RF signal into a 1 or a 0. We're also going to demonstrate that. We'll demonstrate that to you. And then we'll show you at the end how you can convert or remove that signal, that 1 that you received at the end, how you can convert that to a 0. Sorry, to an audio signal. You convert it to a sinusoidal audio signal instead of a square wave. Remember in a previous episode, we demonstrated this practically, but there was a high-pitched sound coming from the receiver that was hard to hear. We played music, we talked through the microphone, and it was really disturbing in the ear. We had a video where we modified that, and it was a little bit clearer. However, what we're going to show you here is actually going to take it even a step further. Without much ado, let's just go and look at that picture, and then we'll go to our simulation. All right, so here let's find that circuit, and then we're going to go and analyze it a little bit. So here is a circuit diagram here. What you have here is the original R433 receiver, the version that we used. So what we did was we tapped the signal from one of the op amps. You have this LM358 op amp that is a dual op amp. So one of the op amps is used as an audio amplifier. The second one is used as a Schmitt trigger. What a Schmitt trigger does basically is it's a comparator. It looks at signal at two terminals and says if this signal is greater than that, then give me a 1. If it's less, give me a 0. So whenever a signal is available at the input and that signal is greater than the reference voltage or reference signal, it will turn the output to a 1. So you get a digital 1 anytime the signal in that input is higher than the signal on the other input. Basically, that's what they're doing. So let's demonstrate that. So what we did was we said there are two op amps. One of the outputs of the op amp is going into pin 5, which is the input of one of the other op amp, which is so we have two op amps. Pin 1 is one output and pin 7 is the other output. Pin 2 is the non-inverting input, and also pin 2 is the inverting input, pin 3 non-inverting input. So pin 5 and also pin 6 are also the other inputs of the other section of the amplifier, the other half of the amplifier. So we are taking the output from pin 1 going into the input of pin 5, and we are amplifying that through LM386, and the signal goes to our microphone, our speaker. So let's go to our simulator, because there we had explained a little bit. We have redesigned the system so you can see all these pin 1 and pin 5 and pin 6 that I'm talking about from this LM386. And then we will show you the modification we want to create. The modification we want to create to make the system work even much better. So let's go to that. All right. So this is the circuit here, as you've seen it on the screen. I am going to run a simulation on that, and you're going to notice what is going to happen. So before I run the simulation, let me show you the full circuit diagram. So here is the full circuit diagram. So here I'm replacing the RF front end with a 100 millivolt AC generator at 200 hertz. This 200 hertz is to represent the audio signal from a human being or from any source. So any audio signal from this source, and then the rest of the components are maintained as is from the circuit, the R433 receiver. The reason we are using the signal generator here instead of the RF front end was because this simulator, the version we're using, doesn't allow us to generate real world signal, um, real world AC signal. But we need an AC signal, and we need a voltage of about 100 millivolts, and hence we just chose a generator like this. So you can go to Multisim, sign up for the free version, and you can play around with these components. So after we've designed it, we have put a signal monitor all through, about 9 signal monitors, so you can tell what we are feeding in, what we are getting at the output, and so on and so forth. So here you have the first half of the op amp, and then the second half of the op amp over there. The first half of the op amp, as we stated earlier, is an audio transmitter. The second half is a Schmitt trigger. So the way this is designed is, if you see this, the inverting input, which is negative input here, so this could be pin 2 or pin 6. The inverting, so let's look at the pinouts. Let's look at the pinout. LM358 pinout. So I think it's easier if I use this to demonstrate that. So let's look at this image here. So when I'm mentioning inverting input and non-inverting input, you can understand a little bit better. Inverting input just means when I send a signal in, the output signal will be opposite phase of what I've sent in. Non-inverting is when I send a signal in, the output signal will be in the same phase as the one that I've sent in. I will draw the picture to demonstrate this. But before that, let's just look at this. Pin 1 is an output, so also pin 7, sorry. Pin 2 is an inverting input, so also pin 6. Pin 3 is non-inverting input, so also pin 5. So there are 2 op amps inside. That's why we call it a dual op amp. Dual op amp. Dual inline packaging for this one here. Dual inline, so the both sides of the IC has equal number of pins, so dual inline, right? They are lined up and they are dual, two sides. There are quad inline where the pins are distributed on 4 sides, but in this case, this is dual inline packaging. And as you can see clearly, there are 2 op amps there. In our first, let me just go back to that drawing. So let's go to that drawing. Yeah, here in this drawing here, we're taking output from pin 5 and then taking it to LM386. Why did we do that? Because pin 5, as you can see here, is a non-inverting input. And that in this schematic, the signal going to this pin 5 came from the other side, pin 1 of the other half of the op amp. So we knew that the signal is already amplified, is outputted on pin 1, and should go to the speaker. But because this design was not made for speaker purposes, it was sent into the input of the other half of the amplifier to function together with other components as the Schmitt trigger. So the non-inverting input, therefore, is connected to the threshold signal or a reference signal. And then whenever that reference signal, whenever the non-inverting signal is greater, right? So whenever the non-inverting signal is greater than the inverting signal, the output is 0. However, when the non-inverting and inverting signal are the same, or the non-inverting is higher, then the output is sorry, when the non-inverting signal is equal to or greater than inverting, the output is high. When the inverting is higher, then the output is low. Non-inverting, so I'm going to write it down because let me go back and put it in the drawing and then explain what I mean by that. And then we're going to do the demonstration. We're going to run the demo quickly. But let's just establish the foundation here, the baseline, before we run that. So I'm going to draw a small box here. I'm going to use that for my explanation. It's going to be my box, and I use it for explanation. So this is input, this is output. So if I have the positive input, positive plus IP is greater than or equal to negative IP. If positive input is less than negative IP. If negative input is greater than or equal to positive input. If negative input is less than positive input. There are different conditions here. So let's analyze what we have in our system. In our circuit here, we are saying if, and we already know that, let's go back to the pinouts. So we already know that in our case, the non-inverting, which is positive input, is pin 5. We are saying when the signal on pin 5 is greater than or equal to the signal on pin 6, so the output should be high. So I just write high here. So when signal on pin 5 is less than the signal on pin 6, the output is low. That's it basically. The rest is the same, just inverting it. So if we were saying if negative signal in negative input, which is pin 6, is greater than or equal to, in this case it can be greater than or equal to, should be greater than, is greater than the signal on pin on the positive input, then it's also low, because these two are basically the same, right? And then the last one should be the same as the top one. So if the signal in the negative input is less than or equal to the positive, then it is high. Again, these two are just the same. So it depends on how you want to explain it. So when I have a signal on pin 6 and that signal is the same as signal on pin 5, my output is high. When I have a signal on pin 6 and that signal is less than the signal on pin 6, the output is also high. Right, so we've explained this now. So let's go back to our demo. And this is going to be very, very interesting. So okay. So did I show this? I'm going to explain it again. Maybe I didn't show that on the screen when I was writing it up. But let me just use a highlighter and explain that. So what we've demonstrated here is, what we're trying to explain here is that we have an op amp that has a positive input and a negative input. That has an output. And we are saying anytime the signal in the positive input, so signal here is greater than, so for that, let's call it A to make it easy. Let's call it A and B. So when signal at A is greater than or equal to signal at B, the output is 1 or high. When signal at A is less than signal at B, the output is 0. This is basically it. There's no further long explanation here. Now let's go to our simulation and try to understand how this play out. So we replicated this design and we're going to demonstrate that with our Schmidt trigger. Very interesting concept. Very interesting concept. And then we'll show you how we were able to modify the circuit and make it function the way we want it to. So I'm going to close this circuit because basically that's what we want to do. And we're going to open this portion because this was added by us for the purpose of demonstration. And then I'm going to run this simulation. Now the simulation is running right now. I'm going to do a split screen, then I'll go quickly to the graph. So the split screen shows you that everything is running concurrently, and then we're going to go to the graph so we can see it better. Right, so what we've done is we put signal monitors all through the circuit, almost like tracing, signal tracing all through the circuit, so we can trace what is happening at each point. And we number them from left to right up to 9 places we took some signals. So we can see, we can turn each of the signal monitors off and see what others are doing at the same time. The first thing I want you to notice is that the amplitude is much more. So let's first of all, let's go ahead and turn off other signals and just leave the. Let me go back to the schematic and show you what we did before we demonstrate this again. So where the signal source is, we have the signal monitor here. Our first probe is on the signal source. So the first probe or signal monitor is in the signal source. And then we number them all through. We have, after the first resistor, we have another probe and then another probe. So they are numbered 1, 2, 3, 4, 5 down here, 6, 7, 8, 9. There are 9 probes throughout the system. 9 probes. So probe number 1 and probe number 9 will show you the first and the last. So let's go to the graph and just remove all the probes except 1 and 9. So remove, we don't want to monitor other signals or the probes. We just monitor 1 and 9. All right, where is 9? 9 must have moved. Okay, yeah, 9 is here. All right, good. So this is 1 and 9. As you can see, the signal really, the amplitude of what we are sending in obviously is very small. It's 100 millivolts. And then the amplitude of the probe on 9, on the signal 9, is about 5 volts. It's 5 volts, which is the voltage of our power supply. So it swings from 0, which is down here, to 5. Anytime there's a positive signal, you can notice that anytime the amplitude is going positive, the output swings to 1. This is the Schmidt trigger. And when it's going negative, it drops to 0. and then back and forth. So let's look at number 2. Let's look at probe 1 and 2. So this is our input signal. It goes through a resistor. So let's look at probe 2. And it's even lower. The resistor lowers the amplitude a little bit. And then let's go back and look at 2. So 2 is right here. 3 goes through a capacitor. So let's go. 3 3 goes through a capacitor. So let's turn that on. It's even lower. The blue line is number 3. It's even much lower. But then let's go to number 4, which is after the amplification. Let's go to number 4. So we're going to turn probe number 4 on, PR4, and you can see immediately there's a huge amplification. I think we turn this off by, yeah, it should be this way. Yeah, this is a modification that I was talking about earlier, and sorry that it was on during the simulation, but I'm going to still turn it off to show you something. The original design was this way. This switch was added by us to simulate something, but you can see instantly the signal jumps, right? This little amplitude jumps to 2.5 volts, or there are 2.8 volts. This is what is happening. So let's go to, that's 4. Let's go to 5. We're going to turn 5 on. Probe number 5. And probe number 5, there's a shift in amplitude because it goes through a capacitor. So it shifts the phase a little bit. And then, but it's the same shape as number 4. So let's look at number 6, goes through another capacitor. Number 6, this is number 9, sorry. Probe number 6, yeah. Probe number 6, yet another shift. And then probe number 7, number 7 and number 7, it seems 7 and 5 and 7. 7 and 5 are the same. So this is 4, and let's go back here. So 1, 2, 3, 4, 5, 6, and 7. So 5 and 7 are the same shape. 5 and 7 are the same shape. The gray and the blue are the same shape. They actually sitting at the same spot, right? So then let's look at 8. Probe number 8, PR8. So it seems that 8 and 4 are the same. Let's see. Let me turn off 4. No, not that. 8 and 8 is this one here, and 8 and 6 yeah, 8 and 6 are sitting on the same spot. So there's 8 right there, and there's 4, 5, 6. 8 and 6 are sitting on the same spot because obviously 8 and 6 you see at the same spot because 6 is just before the switch, and then after the switch there's 8. So 6 and 8 are sitting on the same spot. There's no difference between 6 and 8. Then let's go to 9. You can see how we're debugging this. Now when you go to 9, 9 shows a square wave. And this is the output of the Smith trigger. So when a signal arrives on the receiver, the output gives you a 1. Remember, the design doesn't have all these probes. The design just has 1, which is the signal from the RF front end, and then 9, which is the signal at the output, which is the data out of the R433, the data out. So it just gives you 1 at the output, and then 0, 1 or 0 at the output. And this is why it is doing that. Now, we have explained to you how this is possible. Remember, the signal we have here on probe number 1 is not always there. It's always only available when you send a signal from the transmitter. When you press the switch, it sends an RF burst, which presents a signal to the receiver on the RF front end, which then presents this signal through the amplifications, the first half of the amplification of the LM358 to the input of the second half of the LM358, which is the Smith trigger, to cause these ones and zeros to be replicated on the output of the R433 receiver. So that's how you use it as a remote control device, right? So I'm going to turn everything on now, and you can just monitor it one more time. And then we're going to spend the second half of this elongated tutorial, and we're doing it on purpose so you can understand the theories. We're going to spend the second half explaining to you the modifications we did to this circuit and the simulations we've done. And then in our next video, we will show you in our next video in this series, because we have to actually build this circuit and modify it, so it might take a while. But when we do the next video in this series, which should probably be the third and final video in this series, in this elongated tutorial, we will demonstrate what we're going to show you right now. So let's go quickly and show you our modification. All right, so the modification we did was, we said, first of all, we don't want to build a Smith trigger system because we want to convert the system to an audio amplifier. And as you can see, even without my explanation, that you're getting only half of the signals. Every sinusoidal signal should have the positive side and the negative side, but all we have here is the positive side. The negative sides are truncated because this was not taken into account or consideration during the design. Anytime one is making a design, the purpose, the utility is always paramount in the mind of the designer. Why am I building this? And should I put extra components that are not required or needed? And if they're not required, you don't need them. You don't just need to put components there because you have components. They must have utility, they must have purpose, they must have usage in the system you put it in. Now, because we want to convert this into an audio system, really we have so many other ones, so many other transmitters we've done, so many other receivers we've done, and even we've done transceivers using transistors. But we just want to show, that we can reverse engineer the system to use it to transmit audio, and we have demonstrated that in the previous videos. Please watch the other videos in this series. We've demonstrated that. We've played music from YouTube, we've added a microphone, and we're able to send our voices through that transmitter and receive it on the receiver side. And all we did, the modifications we did, was just connect this LM386 through pin 5 and get the output signal amplified and then play it through our speaker. That's all we did. What you're looking on your screen, that's all we did. Connect this signal to pin 5 and then the rest remain the same. However, if you know us, you know we don't stop there. We have to go a little bit higher, one step further, to analyze and understand why that high pitch signal is almost, always there. It's incurable, if you will, very disturbing to the ear, and we want to remove that problem, and we have found a way to do just that. So let's do that in our simulation. So we started with the simulation so that we can look at the possibilities before we go on soldering or the soldering components, and then realizing that what we're doing are impracticable. But fortunately for us, this is practicable. So let's go there and analyze the circuit. So this is an operational amplifier that was designed basically for the purpose, as we said, of recreating the ones and zeros at the output. If you want to have a full sinusoidal wave coming from this op amp, you need to have a dual power supply. In this circuit, we have a single power supply, and that is one of the problems. So when you send a sinusoidal wave, there's no way to generate the negative half because you have a single power supply. So to fix this problem, you have to create a dual power supply, or you just do what we did. You use a voltage divider to create a virtual earth, virtual ground or virtual earth. So what we did was we pull this pin 4 from, let's go back to the pin out. As you can see, pin 4 in this is the ground pin, negative pin. So instead of leaving it as negative pin, we put it on a virtual earth. We created a virtual earth. So this is what we did. We removed it from earth, so that's why we put it open, put a switch so we can just turn it off. And then after we turned it off, that pin 4 is now connected in the middle of two resistors, 10K resistors connected as voltage dividers. One of the resistors pin is connected to ground, the other end. So the center of the resistors are connected together. The center of the resistors are connected together, and then to pin 4 of the LM358. And then one pin of the one resistor is connected to ground, the other resistor is connected to power supply. So we're going to close that switch. And the moment you do this, let's look at what the schematic, the graph looks like right now. You can see we have a pure sine wave in the output signal, pure sine wave. This tells you that your signal coming to your speaker will be balanced and pure sine wave. I'm going to show you a split screen so you can see the moment I'm flipping the switch. Let's do a split screen. So we have the schematic and then the simulated output, the simulated graph or the interactive graph on the output, right? So let me turn off the switch one more time. I'm turning it off and then turning this on. So I've returned the circuit the way it was built originally. And then I'm going to pull this up and then open this portion that goes to ground, and instantly you have a full sinusoidal wave. So how are we going to achieve this? In our next video, we're going to connect two components in addition to that circuit. We're going to have two resistors in series, one terminal to ground, one terminal to the VCC, and then the center of it connected to the negative power supply of the to the pin 4 of the LM358. That's what we're gonna do, and we're gonna leave pin 5 as is, connected to our amplifier, and you're gonna see what will happen in the speaker. So this theory for now works out well, and we're gonna expand on this theory by building this practically and showing you everything how it works. Now you can still see our Smith trigger is still working. So we're gonna build this circuit. The Smith trigger still works, and then the audio signal will be coming out as full sinusoidal wave. Now there's a reason we put the switch here. I'm gonna flip the switch open, but before I do that, I'm gonna return the circuit to the original design. So pin 4 goes to ground, and then this resistor really wasn't there. So when the switch is flipped open, it wasn't there. So I'm going to turn off this switch in the middle here to see what happens. The moment I turn that off, the Smith trigger, of course, there's no more signal coming there, so it just returns me a high, a 5 steady voltage. And then this one here, of course, this is 8. So 8 and 9 are just steady signals. 8 is giving me 2.5 volts, which is really, why does it give me 2.5? Why does 8 give me 2.5 volts? Because as it were, it's like I am holding this negative signal, and also somehow the input, the non-inverting input, I'm holding it at a steady voltage. And that steady voltage is coming from this voltage divider here. I have 10 kilo ohm resistors, 10 kilo ohms resistors in series, and then I have the center of that connected to both input terminals. So this is determining the balance of this. So I'm holding it at the center voltage, and then the output, which is the ninth probe, is maintained at 5 volts. So it's telling me that the voltage at pin in this case the non-inverting input is either equal to or greater than the voltage at the inverting input. And for that reason, my PR9 is giving me 5 volts. And it's telling me that what I have in the, so maybe I should put another probe here. Let's put a 10th probe. Let's put a 10th probe and see. I'm going to stop this simulation and put a 10th probe. So copy, and I'm going to put it on, I'm going to put it here. So let's see what the 10th probe will give us, what voltage it will give us. All right. The 10th probe is about 2.49 volts. So there are 2.49 volts on the 10th probe and 2.3 on the 8th probe. And for that reason, the 9th probe is now 0. It's now 0. For any reason where the positive input is less than the negative input, the output is 0. And you can see that demonstrated right away. That has just been demonstrated. All right, so let me pull that off and run the simulator. It's going to complain because that probe is not connected anywhere. All right, so stop. I'm going to put it here one more time. All right, you can see the theory we just explained just played out very well. So as long as the voltage here is less than the voltage, so 2.5 almost, and then that voltage on PR8 is 2.3, and for that reason the output is low. So I'm going to play with this resistor to see if I can get them to be equal. Can I do that? Let's see if we can do that. I'm going to move the probe away so I can see the value of the resistor. They're basically the same, even though they're not on the same spot, but the same line. All right, so let me play around with the value of this resistor. So I'm going to try to reduce it and see if the voltage will balance out. So let me increase the value. I'm going to just increase it ridiculously. No, let's reduce that. All right, let's keep reducing that. All right, so there's nothing I can do to get so I'm going to get it back to, all right, as I'm changing the value, the output is also changing. The signals are changing. So I'm going to leave it at all right, let me leave it at 200 because that's what we had in the original design. I don't want to change the original design. All right, so let me turn on the switch then. Let's see. When I turn on this switch, my Smith trigger comes back on. When I turn it off, it goes away. So we've demonstrated this enough. Right, so the other thing I want to do now is keep that on, but then also do a modification. And then I'll turn it off too. So we have the full sine wave on the output. Then I'm going to do the switch close. And our Smith trigger still functions. But then you notice there's a change in other areas. The signal output in other probes are affected. Just a little bit, but still affected. All right, so what happens is it depends on the signal that was received just before the switch was flipped. And right now, the probe number 9, which is our Schmidt trigger output, is high, and it remained high because it was high when I pulled that signal off. So something is going on with this simulator, but you get the idea. What we're gonna do in our next video is 2, and you can do this before us. There's no secret here. What you can do is go ahead and pull that that pin 4, which should be this pin here. The good thing here is that the pin is on the outside, so you can desolder that and pull it up, and then connect a signal from there. Connect a wire from there to the center. So we're gonna do something like this. We're gonna have 2 resistors. This is gonna be grounded, and this is gonna go to the positive, which is basically here. And then we're gonna connect the center of this. Let's use a different color because we're gonna be transversing a lot of areas. We're gonna go all the way to here. The rest of the things remain the same. We're gonna have these 2 resistors, R1 and R2, where R1 is equal to R2 and equal to 10K. All right, this is where we're going to be ending this today. So do this and you'll see the audio will be very clear. If you haven't done it until we come back with our next episode on this series, we'll demonstrate that and you can see it clearly. All right, so remember to like and subscribe, share this video, and remember to always come back to our channel. We're going to be uploading more videos subsequently. We've just been busy with other things, and but we're going to prioritize this channel. Remember, it's very educational. What we're doing here is educational, and everything we teach on transmitters and receivers are just for educational purposes only. Use that to learn the theories. Use that to learn how things work. I'm interested in how things work. I'm just an enthusiast of how things work, right? So spend your time learning how things work. Maybe we'll be talking about ChatGPT and other emerging technologies very soon. But for now, let's just concentrate on how things work in the electronics section, the electronics world. For now, I like to learn new things. I like to learn how things work. Check out our channels on websites, on web application designs and other mobile application designs, Android application designs. Check out other things we're doing, and like, subscribe, share, come back, comment. Let's hear from you. Let's hear from you. All right. All right. Thank you for sticking around to the end. Until we come your way again with more contents, stay enthused.